Okay, good afternoon, everyone. Thanks for still being here with me at this very last moment. My name is Zhang, and I'm from Temple University. Today, I'm going to talk about randomization or condensation, linear cost matrix sketching via cascaded compression sampling. And here are my collaborators. As we know, scientific discoveries of human beings have undergone different stages. In ancient times, science was empirical, which was used primarily to record very simple natural phenomena. A few hundred years ago, theoretic branch of science grew rapidly, allowing us to have a much better understanding of this natural world. A few decades ago, the invention of computers makes computer simulation a very powerful tool in those problems where models grow over-complex and analytic solutions become impossible. And nowadays, we are confronted with a new path towards science, data-intensive research. Scientific breakthroughs nowadays relying more and more on our capacity to store, manipulate, and extract knowledge from massive data. And in this talk, I'm going to focus on matrix low-rank decomposition, which is a fundamental building block in modern scientific computing and big data applications. Here is the outline. I'll first give a brief review of randomized algorithm, which represents state-of-the-art in extracting structures from massive data. I'll point out several challenges for randomized algorithms. And in order to address these challenges, we propose cascaded compression sampling, which we believe is the first linear time and space algorithm whose performance can rival the quality of state-of-the-art randomized algorithm, which consumes at least a quadratic amount of resources. And numerical evaluations and conclusions will be provided following that. Okay, matrix low-rank decomposition, as you probably have been very familiar with, or sometimes called matrix sketching in certain scenarios, is aimed at factorizing a large matrix A into the product of smaller rank factors. It can greatly reduce the problem size and dimensionality, and it actually has drawn considerable interest from several interdisciplinary areas, including machine learning, data mining, theoretic computer science, optimization, and numerical linear algebra. Here, I will just simply mention a few applications like information retrieval, recommendation systems, as you have seen from previous talks, and model compression in deep learning, manifold learning image processing, and kernel methods graph-based algorithms. Okay. So I think probably you have heard these two algorithms for randomized SVD. The first one is random projection method. Basically, given a large matrix A, it first multiplies A with a template matrix, or which is Gaussian randomly distributed, or it can be a fast transform. And then QR decomposition is used to extract the column basis from Y. And finally, matrix A can be approximated as Q prime and A multiplied together. Here is the approximation bound. Basically, it states that the larger the template, the more information you can extract from the data. The second one is the CUR decomposition proposed by Honey and Drinis. The idea is very simple. Basically, it first samples a subset of rows and columns, which is denoted by R and C, and then it computes intersection matrix U by multiplying the pseudo-inverse from C and R on both sides of A. And here is the probabilistic error bound that says with high probability, the approximation error can be at most 2 plus delta times the optimal one. Randomized algorithms have gained huge success in recent years. However, there are still big challenges lying ahead of us. The first is the challenge, the big gap between theory and practice. As we know, probabilistic sampling or those sampling schemes using leverage scores, although they are more expensive and equipped with tighter theoretic error bound in the worst case, their performance can be very similar to random sampling, or sometimes even worse than random sampling. The second limitation is the memory bottleneck, because as we have seen that all these existing randomized algorithms have to multiply the matrix with a template. And as a result, it has to access the entire input matrix. For example, I'll give you an example here. This image is is taken by the Hubble telescope. It has 15,000 rows and 13,000 columns. Storing this matrix alone already takes several gigabytes of memory, let alone the expensive operations defined on top of it. Okay, in order to solve these challenges, we propose our algorithm framework called Cascaded compression sampling. Before that, I will first introduce some very well-known existing algorithms. The first one, the Nystrom method. It was originally designed to approximate the kernel matrix. For example, given a set of input data X and the kernel matrix where the ijth entry is the similarity between xi and xj using kernel function, Nystrom method can select a subset of rows and columns, which is denoted by E and E prime with intersection W, and then approximate K using this multiplication, which is very elegant framework. The nice thing about the Nystrom method is that instead of performing sampling on this n by n kernel matrix, it can perform sampling simply on the n by d data, which is much cheaper and basically linear time and space complexities. And different sampling scheme has been studied in the literatures. And here is in a probabilistic error bound. You might be wondering whether the Nystrom method can be generalized to a rectangular matrix because it has very nice properties. It only has to access a very small number of rows and columns in the data. That means it does not have to even access the entire part of the input matrix. And the answer is yes. Here we will borrow the structures of COR matrix decomposition to subsume several existing algorithms, including Nystrom method and its generalizations. Recall that the COR decomposition wants to factorize a matrix A into the product of CUR. And here we have two rounds of sampling. The first round is called source sampling. That means it selects a subset of rows and columns as basis, which is exactly C and R. And in order to compute a U, we will do a second round of target sampling. The role of target sampling is to compute the matrix U by specifying on which subset of A the approximation error needs to be minimized. For example, here, the green sampling actually specifies this two yellow matrix, and when they are multiplied together with U, they need to minimize the approximation error on the orange part. Different existing algorithms can all be subsumed in this simple framework. For example, in the Nystrom method, the source and target sampling are chosen as the same. In this case, intersection U is simply the inverse of W. In the sketch COR proposed recently, the target sampling is performed independently compared with the source sampling. And for the COR decomposition, actually it's very aspirant. It tries to minimize the approximation error on the entire input matrix. It's more accurate, but much more costly. Okay, so next we will be focusing on the Nystrom method, the generalized Nystrom method on rectangular matrices where the source and target sampling are chosen as the same. Basically, it can be simply put as A is approximated by C, pseudo-inverse of W, and R multiplied together. The most important idea of our approach is compression sampling, which is based on a very interesting underlying connection between matrix lowering approximation and data encoding. Suppose we're given a matrix X, and for the sake of argument, we assume an exact decomposition for this moment, P and Q prime. They might not be low rank. And our goal is to select a subset of rows and columns from X, which naturally corresponds to the rows and columns in P and Q prime. And our theoretic analysis shows that in order to approximate X accurately with the generalized Nystrom method, the selected rows and columns in P and Q prime should be the representative ones. What do we mean by representative? Basically, it means that the error of encoding each row in P with the closest landmark rows in P that we have selected should be minimized. Basically, this is very similar to a k-means clustering algorithm. And here we have shown that the low-rank approximation error on the entire input matrix is actually upper bounded by the column and row sampling errors. Here, ER and EC are exactly the encoding errors of representing the rows and columns in P and Q prime, which are exact low-rank decomposition for this moment with the selected ones. Here we have visualized the relation between the row and column sampling, which are the horizontal and vertical axis of each point. And because we have tried many different sampling, some are good, some are bad, and so their encoding errors vary a lot in this plane. And each point is color-coded with the approximation error of the entire input matrix. As we can see, the low-rank approximation error correlates very well with the row and column sampling errors. So this motivates us to use k-means clustering as a sampling scheme. However, obtaining an exact decomposition P and Q prime is anyway meaningless because it's exactly our final goal. So in order to make this whole thing practical, we have resorted to a two-step procedure. Okay, which we call a cascaded compression sampling. It has two rounds. The first round is called pilot sampling sketching, which is used to generate a very, very coarse representation. And the second round is called follow-up sampling and sketching. Basically, we'll first randomly select a subset of rows and columns from the input matrix, and then we apply the generalized Nystrom method, and we will further orthogonalize the columns and rows. Here, U and V prime are the orthogonalized version of the C and R, and multiplied with, each of them is multiplied with the square root of the singular vectors. And then U and V prime here, they are actually can be considered as a embedding of the rows and columns of the original matrix. And therefore, we will perform sampling in U and V prime separately using k-means clustering. And then through this clustering, we pick those clustering centers, and we'll pick those rows and columns that are closest to this clustering center. And this tells us, okay, you should perform a second round of sampling, and you should sample these rows and columns, and they are fed into the generalized Nystrom method again to achieve the second round of sampling. So this is our overall algorithmic framework. As you can see, the algorithm is computationally very efficient because it only needs to access twice a small number of rows and columns in the matrix. The first time is uniform sampling, and in the second round, the algorithm will tell you which rows and columns should be selected. And what can we say about this cascaded compression sampling? Obviously, as a two-step method, we hope that the second round will generate a better solution than the first round, and this is exactly we can prove. Basically, we have shown that the error bound of our approach can actually it drops from the first round to the second round. That means it becomes more accurate, and this drop of error bound across these two rounds is actually closely related to the drop of the encoding errors in the second round. Remind that we are performing k-means clustering, and it can reduce the encoding errors. The higher the drop of the encoding errors, the higher the algorithmic boosting. So we call this algorithm boosting because by cascading two very simple linear cost sampling routines, we are actually having a much more accurate solution which can rival the quality of quadratic cost algorithms. Before jumping to the experimental evaluations, I want to talk about some details, which I believe is very important. First, we find that the dense matrix and sparse matrix have very different embedding behaviors. For example, in the left figure is an image, the left singular vectors of an image. We can see that the energy of this image is actually distributed more or less uniformly across all the rows and columns. And the right one is the left singular vector of a Word document matrix. Because of the power law distribution, many rows or columns are simply filled with a majority of zeros. As a result, the embedding of these rows and columns will be collapsed towards the origin. As you can see from the histogram on the right figure, the green bars, many points are actually very close to the origin. Of course, if you why? Because the distance between each point to the origin, or their L2 norm, is exactly an upper bound of the original norms in the rows and columns of the matrix up to a global scaling. So of course, if you use k-means sampling, you will waste a lot of clustering centers close to the origin, which is a waste of sampling quota. And in order to correct this, we will propose a weighted k-means sampling. The idea is very simple. Each point is no longer uniformly weighted. The weighting is chosen as the norm of this point and subject to a linear or nonlinear function. So by doing this, you can see that the k-means clustering centers are pushed apart from the origin. The second problem we observe with the Nystrom method, it can easily overfit. And this problem has long been ignored in the literature. For example, the Nystrom method is very nice in that it only has to select a subset of rows and columns. So we tried it on the on this image, and the yellow lines represent our sampled rows and columns. However, if we simply plot the reconstructed image, we find that it's actually very poor. A closer examination shows that the reconstruction is exact on those selected rows and columns, but actually very poor outside those selected rows and columns. Actually, obviously overfit happens here, and here we further examine more details. Here, the two figures are the approximation error versus the strength of regularization. Basically, the larger the regularization, the ratio here, that is number of singular vectors used in computing the pseudo-inverse, will approach to 1. You can see that the problem is very difficult because for dense and sparse matrices, the optimal rank actually is data dependent, and it changes from data to data. So of course you can use a simple submatrix for validation, which works pretty well. But here we propose a simpler approach. Basically, remind that the matrix A is approximated as this one by decomposing the intersection matrix W as UW sigma W VW prime. And here the left part is actually the extrapolated left singular vectors. Instead of, they are using the first extrapolate VW, which is the right singular vector of W, by using the column C, and then normalize it with the inverse of sigma W. But instead of using this normalization, we will simply compute the norm of each column in C, and then we normalize it with these norms. We call this norm-based regularization, and it actually works pretty well in practice. You can see that the red line and the dots actually is our approach after stabilization. It doesn't have to throw away any singular vectors, and it always achieves the minimum errors. Okay. Now we can examine the experimental results. We have compared with a number of approaches, linear cost algorithms and quadratic cost algorithms. And we have worked on a number of data, including a very large image matrix, very dense kernel matrix, as well as a sparse Word document matrix and movie rating matrix. here is the result of the linear cost algorithm. They are all linear. We can see that here the green curve is our pilot sketching result, and the red curve is our follow-up sketching result. Obviously, we can see that on both dense and sparse matrices, there is a improvement of the approximation quality at the cost of a second round of linear cost algorithms. And in the second part, we compare our approach with randomized algorithm, which are state-of-the-art algorithm, but they are quadratic cost. We can see here the green one, the green one is the random projection method, and the orange one is the sparse random projection, which are state-of-the-art algorithms. Well, our the horizontal axis is time, and the vertical axis is the approximation error. We can see that by consuming the same amount of time, our approach actually achieves a much lower approximation error. And the second set of results on dense kernel matrices. And here we can see that our approach is particularly more efficient because it doesn't have to compute the entire kernel matrix. It only has to compute the kernel matrix on the fly, while all other algorithms here will have to be fed with the entire kernel matrix. And the last set of results are on sparse matrices. As we can see that, again, we did observe a very large improvement in terms of the balance between time and accuracy. Okay, so to conclude, we have proposed a new sampling paradigm called cascaded compression sampling. It only has linear time and space complexities, and it's more accurate empirically than the existing randomized algorithms. And it achieves a very nice algorithm boosting properties by cascading simple sampling and sketching routines. And in the future, we will definitely try this new sampling paradigm in a number of different applications, and we will also extend it to tensor problems as well as parallelization. And currently, we are already having a parallel version of this approach. Okay, thanks very much for your time, and I'll be glad to take any questions or comment.